Slack too, but I received questions about using your field card on the weekend, aside from the one field you get Saturday lunch. And the first thing that they told me was you can't do that, and then several of you experimentally discovered you can do that. So what they told me now is you can swipe at any time, but you have a fixed number of fields. So if you skip meals during the week, you can use them on the weekend. It is not our responsibility if you run out of meals by using too many on the weekend. So the ones you're provided are, I think it's 60 total. Yeah.
If does that also mean you can use your one weekend meal at a time other than Saturday lunch?
Yes, I think you can use it anytime you want.
Okay.
I should double check the hours of the C4C. Yeah, I think if you do run out of meals, try not to run out of meals. If you do, you can take a credit card to get it. Okay, that's all I have. So with that, I'll turn it over to Pat.
Okay, so thank you all for braving 9 a.m. And we're going to try to get through as much as we can today. I realize that at the pace I was going, I probably really needed a fourth lecture, but we're going to get as far as we can. And as promised, there are stickers for all of you that braved 9 a.m., so we'll do that at the end. Okay, so let's get started. Now, I'm going to spend a little time just covering a last topic that's really needed to kind of set the stage for what the future is. Now, I know as theorists, and myself included, this is very kind of accelerator focused, not physics focused in terms of these lectures. Obviously, kind of the answer is if I can give you an accelerator with higher energy and higher luminosity, you obviously can do great physics with it. I'll cover that at the very end, just using a few quick examples. But as I said, my motivation for these lectures was really to give you an appreciation of where we are and where we're going with technology, because that's what drives everything. So what we've done so far through the first two lectures is come to the conclusion that there's really two types of modern particle accelerators, high energy particle accelerators. Okay. There's still all those other accelerators I talked about that get used and all the other 30,000 accelerators out there. But in high energies, there's essentially the linear colliders, the LINX, or the circular colliders, which we talked about at the end of class last time, the synchrotrons. Okay. And both of these are based on RF accelerating technology. Okay. Now, one thing I didn't have time to get into much detail is we talked about the RF cavities and how that's the modern design for it, and you get the synchronization. But there really are two different versions of RF cavities. There's normal conducting, and in the last 20 years or so, superconducting cavities can now be built. They do the exact same thing. The only effective difference between these two things is that the cavities have a lot higher quality factor for their resonances, for superconducting cavities. So essentially, you can put a lot more power into the cavities for superconducting cavities compared to normal conducting cavities and not have to pay too much money because they're much more efficient because of the resonance. Okay. Now, the point, though, at the end of the day, since we haven't talked about the particular particle type, is you might say, why would anyone build a LINX ever? Okay? The synchrotrons are absolutely fantastic because you can make them smaller. Okay? You don't have to keep extending to Kansas to get to the TeV scale. You also don't have to build as much RF, okay? Because you keep going through the same thing over and over and over again. So you can build fewer RF modules, and therefore they're more power efficient and more sustainable as well, okay? So the question is, why would anyone build a LINX? Well, now we have to go back to our formula for the energy gained in a synchrotron. And we wrote that down as the change in the energy of the beam per turn. Okay. This was just our potential for our cavities and then the effective phase that they see as they go through the cavities. And this was the benefit that they keep just accumulating this as they go around and around and around. So as long as you use stable particles, I can in principle reach higher and higher energies. Now, the one thing that we didn't talk about is, I said in response to one of the questions, there's also potentially an energy loss term, okay? And this is the concept of synchrotron radiation. So we know that whenever you take a charged particle, even in the most straightforward, non-relativistic version of electromagnetism, when you take a charged particle and you accelerate it, what happens? You get radiation. Okay? You don't need to do anything fancy about colliders. You take your Griffith C&M or whatever, or you get the formulas in your freshman physics, and you say, oh, charged particles that are accelerate, radiate, and you learn, for instance, the Larmor formula for radiation from a charged particle. Now, this works, and I'm not going to put the prefactors, but essentially, this just says that the power radiated is going to be proportional to the acceleration squared, okay, for a classically accelerated particle. What this means is that in any of our colliders that we've been talking about, we've ignored this entirely so far, we are taking a charged particle at rest, and we are bringing it to astronomical energies, hopefully, okay? So that implies a lot of acceleration that charged particle has undergone. So therefore, along the way of this whole acceleration change, we have the potential to be radiating, losing energy the entire way. So the question, though, is how much energy is actually lost? I blissfully ignored that term there, and I also blissfully ignored it for linear acceleration, okay? In principle, you always have acceleration due to, you always have radiation due to the acceleration of whatever particle you're accelerating. Now, if we were talking about a collider, we're no longer in the non-relativistic limit where we can take our Larmor formula from Griffiths or your undergrad first year book. So what we need to do is look at the relativistic limit. Now, let me not use this board. So the relativistic limit of the power radiated by a charged particle when it's accelerated, essentially the only difference that we have to keep track of is the fact that we're no longer using a 3-vector in time. We're now having something that scales like dp mu d tau squared, okay? So this is our relativistic version of the acceleration formula. Now, this is a little bit trickier than just our non-relativistic version of it because we have to keep track of both dE d tau and dP d tau, unlike the non-relativistic version. But what we can do is we can take the general formula for radiation and we can look at the two specific limits of accelerators that we're talking about. We have linear accelerators and we have circular accelerators. So what we can do is look at two different cases. Our linear accelerators, okay, they have the fact that our dV, d tau, is going to be parallel to the velocity, okay, because you're just accelerating in a line. Whereas our circular accelerators obviously have our dV d tau will be perpendicular to the velocity, okay? I'm assuming we're at relativistic speeds and we just have to care about that direction. Now if we take the formula, oh, this one got stuck. Something grinding there. Okay, we'll just leave that one there. So let's go up here, and if we take the power radiated formula for dP d tau in these two cases. For our linear case and our circular case, we get formulas that simplify in the following way. That our linear case is our power radiated goes as 1 over the mass squared of the particle, dp dt squared. And our circular formula looks very similar, except we pick up an extra factor of the boost squared. Okay. Now, it appears that the only difference between linear and circular at this point is just this extra factor of the boost. We just have to evaluate what dp dt is. But now we have to actually think about the fact that we are traveling in a straight line or in a circle. So we can evaluate these formulas a little bit more carefully. So for a linear acceleration, well, we need to understand what is our dp dt set by. Okay? So this is a force on the particle. Now, what we used to figure out what the energy gain of the particle was, this is just the work done on the particle. So our dp dt is simply our dE dx. Okay? So in other words, we can simplify our radiation formula in terms of an abstract quantity that we don't know in terms of the acceleration. But dE dx, this is exactly what we've been calculating for accelerators the entire first 2 lectures. So in other words, the power radiated in a linear accelerator looks like 1 over m squared dE dx. And this just sets the gradient that we're going through, squared. See, Tom. So this depends on the mass of the particle, what particles are accelerating, but it's really set by the accelerator parameters in the sense of like what our RF cavities are. Okay, what is our gradient that we're experiencing? So naively, nothing seems that different about circular except for the gamma factor. But now let's think about this. If we're really in a circular orbit, what's happening? Well, we're not actually changing the momentum, we're changing the direction. If I'm just imagining going in a circle without accelerating for a second. And so therefore, we're saying our dp is really just our p d theta. Okay, we're changing the angle as I go around. So in other words, dp dt is just going to be p times our frequency that we go around in our circle. And if we approximate this as a constant circle, which is what we're hoping to do, this is just PV over R, which R is the bending radius of the entire synchrotron that we're talking about. Okay? But now we can plug into our formula, and we see that the power radiated for the circular collider so we have this factor of gamma squared over m squared. Well, gamma we can replace by E over m. Okay? So we get something that looks like an E squared over m to the 4th. And then our dp dt needs to be squared. Well, for relativistic velocities, p is just the energy. Okay? And the radius is there. So we get a factor of E squared over r squared. Okay? So naively, we start from, well, we do start from the same radiation formula, but depending upon how the acceleration, whether it's linear or whether it's circular, we get things that based on the machine parameters are entirely different. Linear acceleration only cares about the gradient that the particles experience going in a straight line. The gradient doesn't appear anywhere here. This depends on the absolute energy of the beam and the absolute size of the collider, neither of which appeared in the linear formula. So, oh, now it's completely jammed. Okay, I'm going to switch to this side because that's a good point to leave those formulas up for a second. So we can ask, what is the power radiated in a linear accelerator? Do we care about this quantity or not? Okay. Now, I've dropped some prefactors there, but what we see is that the power in a linear accelerator, this is just related to the d/dx of the machine. And if you actually think about what is the power radiated in a linear acceleration, first, what is the power inputted into a linear acceleration, okay? Now, the power inputted, that's just our d/dx, right? That's how much we're putting in. We'd multiply that by the velocity of the particle, and that turns into a power. Okay, that's the energies or d/dx. So we can evaluate this for a linear accelerator, and if you put in, for instance, the mass of an electron and typical gradients, you find that the power radiated compared to the power input is about 10 to the minus 14. Okay? So in other words, even though both linear and circular accelerators are undergoing acceleration and giving you radiation, linear acceleration, you don't care at all about the power loss compared to however you do it. However long you do it, it's still going to be negligible. Now, the unfortunate part is that power radiated for the circular doesn't have that same sort of scaling. We don't see the d/dx. It depends on the absolute machine parameters. It also tells you, for the first time, that there is a strong dependence on what the mass of the particle that you're actually accelerating. Okay? Now, it appears here too, there's a mass dependence, but as I said, for an electron, it was tiny in the first place. Okay? Now here, what we see is, for instance, if I look at the power radiated in a synchrotron, if I choose two different types of particles, okay? So let's, for instance, choose an electron and a proton. Well, if I assume that the electron and the proton are in the same radius and with the same energy, then the only thing that this depends upon are the mass of the particles. So this looks like the mass of the proton over the mass of the electron to the fourth power. Okay? And in other words, what we have is a GeV, let's say over 0.5 times 10 to the minus 3 GeV to the fourth. And this is a whopping big number very fast. We get a difference of about 10 to the minus 13, or 10 to the 13 in terms of electron to proton. So electrons radiate 10 trillion times more than a proton in the same collider. Okay? Now, okay, that's fine, but the next thing you should ask is, does it matter absolutely? Okay? This was the calculation we did for linear accelerators. Even though they both appear to depend on d/dx, the actual, when you plug in, it looked like 10 to the minus 14, and I didn't care. So if we want to understand the power radiation in terms of absolute quantities, well, let's think about a quantity that we kind of have a more intuitive nature for in terms of, rather than just absolute power, what is the energy loss as I go around a turn? Which is a formula that's now been erased, okay? So we want to compare to the energy gain in a synchrotron compared to the energy loss. So the energy per turn that I lose due to synchrotron radiation, well, I just need to evaluate my integral over my power loss. Okay. And for our perspective, that's just going to be given by what is our radiation formula, and then the time it takes to get around a turn. So this, in the relativistic regime, will just be our synchrotron formula times 2 pi r over c, okay, because we're saying we're relativistic. And so this gives us essentially the same formula we just had, our e to the fourth over m to the fourth, but we get to gain back 1 power of the radius, okay, by going around the beam. Now let's plug in actual numbers to see what is the energy loss compared to the energy gain from going around. So we need to pick some parameters for the energy we'd like for collider to be. We can choose, for instance, an electron and a radius. So the highest energy E minus and E plus beams ever created thus far we're at the LEP-2 collider, okay? And they got to roughly 110 GeV. So there are runs starting from 90 GeV is LEP-1, and you increase energy to 2 MW, and then eventually to 220 GeV. But for our purposes, let's just take our energy to be 100 GeV, okay? We'll use the mass of the electron, which is our 0.5 times 10 to the minus 3 GeV. And the radius of LEP, okay, this is just the same LHC tunnel, just being used over and over again. So the radius, I'm going to give it in meters. So this is roughly 3 times 10 cubed meters. Okay. Now we still need to plug into this absolute formula to get the quantity. So delta E, I'll give in per turn. I'll give in KeV, is approximately 10 squared e to the 4th in GeV to the 4th over R in meters. Okay? So if we put in the LEP parameters, we've got a 10 squared, we've got our factor of 10 squared to the 4th power, okay? So now we have 10 to the 10, and our radius is in meters, so we get our factor of roughly 10 to the 7th KeV lost per turn. Okay? Or in other words, about 10 GeV. Okay? So if you thought you had this nice beam circulating around at 100 GeV, okay, every time you go, okay, and this is very quick, right? You're going at the speed of light and going in a circle that's 27 kilometers. Every time you go around, you lose 10 GeV. So if you think about this, I only have to take 10 laps and my electron's back down to 0 energy. Okay? That's absolutely disastrous if you wanted to make a collider that you could then keep colliding things over and over again to have some luminosity to do this. Okay? So the only possible way out is for a circular electron collider to continually add more and more RF into the system. We have to add more and more power. So the point of the synchrotron was we needed less RF because we could keep using it over and over again. But now since we're losing so much, we have to keep adding more and more RF elements and keep powering them to keep the beam up. So essentially, circular E plus E minus colliders are going to hit a wall where you have to put more power in than you lose, and that balance is going to be the wall that you're going to hit to, okay? Now, of course, since we already did this calculation, if I did the same collider with a proton, well, I have a 10 to the 13 factor for electron versus proton. So that's why, for instance, at the LHC, where I have, if I think about the same parameters, although the energy is higher, this factor of 10 to the 13th, I'd lose less than an electron volt, right? I'd use like 10 to the minus 4 electron volts, okay? There'd be no loss for a proton. So protons or any other heavy particle can get around this issue of synchrotron radiation, but unfortunately, circular E plus E minus colliders can't. Now, this tells you that you don't want to use them at super high energies, but this also is why there's so many of these out there in the real world for colliders other than high energy particle physics, okay? You can use electron accelerators as synchrotrons, and what they're doing is this energy you're losing, the power you're radiating synchrotron light, okay? So pretty much every E plus E minus collider in its early days was used for some particle physics experiment. They've now been repurposed to materials science and condensed matter and industrial applications to use this very high energy light source, okay? Now, that means that if we go back to our formulas, there is only really one option to go to high energy with linear colliders, because we don't lose this extreme amount of synchrotron radiation and have our power budget skyrocketing, okay? Now, the problem though with linear colliders we talked about and why everyone should build a synchrotron if they can is the fact that I don't get to reuse the RF, So I have to keep powering the entire section of the linear collider, and I have to keep building the linear collider longer and longer. So we get to essentially a fact that we have circular colliders are proton colliders, and linear colliders are for E plus E minus colliders. Okay. Now that will let us set the stage for what the current and past prospects for all the various colliders as a function of time. So on this graph, this has lots of colliders that have already existed, okay? And then what is the potential future for the field, okay? And what you see here is you have a number of projects, so FCC and CEPC. These are circular colliders, circular E plus E minus colliders, okay? Now, they essentially can't go beyond a few hundred GeV because of this energy loss. And in fact, the only way to get around this energy loss is possibly to go bigger, okay? So both of these are order 100 kilometer sorts of colliders, the FCCE and CEPC. Linear colliders can potentially go higher, okay? But again, we have the issue that since linear colliders need more RF power, because our gradient is fixed, and they need longer tunnels, you essentially hit a wall, okay? We can get roughly to a few TeV before practical considerations come into effect. So we talked about the practical consideration of the length of the collider last time, but to give you kind of some numbers, so the highest energy prospect for a linear E plus E minus collider is the CLIC project, Compact Linear Collider. Now, Compact Linear Collider can get up to roughly 3 TeV, as I said. It's not that compact. This is a length of about 54 kilometers, okay, so twice the LHC. And what is the power? Okay, you're not losing the synchrotron power, but you still have to power the RF the entire way down this 54 kilometers, okay? And so to give you an idea of the power budget of CLIC, if it was built, the power budget is 580 megawatts. So depending on what level of theorists you are, I mean, these numbers might mean nothing to you. To give this a little bit more context, so the power of Boulder, Colorado, okay, this one was harder to find. I don't know if it's right, Tom, or somebody locally can tell me if this is orders of magnitude off. But you look for sustainability, and by 2050, they want to replace all power with sustainable power, and the claim is you need renewable power at the level of 175 megawatt. Okay? So this gives you a context for how power hungry these colliders are, okay? This is several times the entire power consumption of Boulder. To give you a number that I'm a little bit more confident on, the power of New York City, this is about 5.5 gigawatts, okay? But here you're serving order 10 million people, not just a collider physics project, okay? So this is a great concern going forwards, okay? We're running into cost issues in terms of these colliders become so long, okay? Remember, this is order 100 million to a billion per kilometer, okay? And we also run into power issues. So that's why there's this wall here for linear colliders. So from this perspective, it appears you could go back and then ask, why would you ever build an E plus E minus collider? Okay? It has no real prospects for going to very high energy using technologies that we can build currently. Now, the basic difference, though, is it's not just about the power, the cost of these colliders, the energy you can get to. The real question also is, what's the physics that we can get out of any of these machines as well? So for instance, if I think of a proton-proton collider that can go to high energy versus an E plus E minus collider that's stuck at lower energy, remember that protons are composite. Okay? So that implies two things. Well, I'll do three things. One, you only get to use a fraction of the energy. Okay? If you think about the average PDF, you're kind of, if you want to take a valence quark off, you're talking about x's of 0.2 to 0.3. You got lots of gluons at low energy, but at the very highest energies, you're kind of petering off after roughly a tenth of the energy scale. So that's why even though the LHC is a 14 TeV collider, what we're really probing up to is roughly the TeV scale. The other side of this is, since protons are composite, they have very, what I'll call, messy collisions. Okay? You're smashing these bags of quarks and gluons together, and you have lots of detritus that comes out of a collision. So it makes it very difficult for detectors. And last but not least, because they're underlying strongly interacting particles, you have lots of other background processes. The rate for backgrounds are very large. So we can show this in terms of a picture. Let's look at, for instance, a Higgs event at Atlas versus a Higgs event at a potential E plus E minus 250 GeV collider. And notice there's an extreme amount of tracks in radiation deposits in your calorimeter versus you could actually buy, that's a Higgs, okay, at an E plus E minus collider without having to do any fancy analysis. Okay? Now, of course, this will get mitigated as our computational power gets better and better, okay, in terms of your lectures on machine learning. But there's also the fundamental issues of, can your detectors withstand the radiation that you're experiencing with all these particles? Can you build a detector to contain them and to bend the particles like we talked about? Okay? So E plus E minus colliders have a role if you have a very specific target, like the Higgs target. Okay? So that's why if we go back to this, even though we talk about trying to get to the highest energies with E plus E minus colliders, really all of these projects have a Higgs factory stage inside of them, where you roughly run at 250 GeV, where the largest ZH cross-section is. Okay? But there's a subtlety to all this E plus E minus collider talk, which is, yes, we're not able to go to high energy with E plus E minus colliders. We can have this clean environment. But let's go back to our discussion that we had about higher dimensional operators on our first lecture day. Okay? So precision versus energy. Okay? So at a linear or circular E plus E minus Higgs factory, okay, all of these, based on the technology, roughly produce about 1 million Higgses. Okay? Now, if we think about if we have no backgrounds, because they're so clean and they're not strongly interacting, what it says is that E plus E minus Higgs factories roughly tell you that the precision that you can measure on the couplings of the Higgs to any standard model particle, like fermions or vector gauge bosons, okay? This gets you roughly to the 1% to the 0.1% for the best measured couplings like the HZZ coupling, okay? This is a great improvement over the LHC. To give you a kind of a context for the LHC and the high luminosity LHC, this is of order 1 to a few %, okay? So you can really get an order of magnitude more here, okay? But let's go back and think about, what does precision actually mean if we're trying to study the Higgs in great detail, if we wanted to make a factory for one of these things? Well, what we can do, since we're not probing high energies, we can always think of Higgs precision in terms of an EFT. Okay. Whatever the new physics is at high scales that modifies the properties of the Higgs or explains why the Higgs exists, or many of the numerous questions around the Higgs, we can always think of this at lowest order as some dim6 operator. Okay. And so essentially, you can take any renormalizable coupling in standard model, okay, and we can add on to it. It always will have a dimension 6 analog, which looks like h dagger h over m squared. Okay? So what does this mean for the characteristic size of deviations for any Higgs couplings based on some RG flow to low energies? Well, this means that our precision on our couplings should roughly scale like v squared over m squared with some possible couplings in front, how this couples to the Higgs. Now, what this means, though, is that since we know the scale of the VEV of the Higgs of order 100 GeV, what Higgs factories are probing a mass scale that's roughly 1 to a few TeV. Okay? Obviously, if I have a weaker coupling, it's probing an even lower scale where the effective field theory might not even be valid. But if I go to strong coupling, I'm not probing astronomically high energies. Okay? This is the same sort of argument that we talk about the EDM. Yes, you in principle could be probing 1,000 TeV, but if you think about how it scales, you're really probing a much lower energy scale. Now, this, of course, means that I have the option to do a Higgs factory, but if I could just go to higher energies, I could cover the same physics. Okay? So again, we can come back to the question, why would you build an E plus E minus Higgs factory? Okay? If I could just build a higher energy collider, why don't I go ahead and do that? Okay. Now, we need to think about what it would mean to build a higher energy collider. So luckily, we don't seem to have any impediment other than it takes a long time because it costs a lot in principle. We can build them as synchrotrons, but what was our synchrotron condition? Okay? Our synchrotron condition was that the radius of our synchrotron collider scaled as the energy over the magnetic field. Okay? And the beauty of the synchrotron was I had to keep these things synchronized so that the beam stayed in an orbit. So what this means, though, is if I want to take something from the LHC scale here and jump another order of magnitude in the energy of the beam, I have essentially two options. Okay? If I'm increasing the beam by an order of magnitude, what that means is if I wanted to do it at the same size, I would need to increase the B field by an order of magnitude. Okay? The B field of the LHC, as I said last time, these are steered by 8.33 Tesla dipoles. Okay? And this is the absolute bleeding edge of superconducting magnet technology when the LHC was built. Okay? So I clearly can't just change this by an order of magnitude and put 80 Tesla magnets and then stick in the LHC tunnel. Of course, the other option is let me take this and increase the radius using current magnet technology. Well, that would mean that I have to increase the size of the LHC by an order of magnitude. Okay, so now we go from a 27 kilometer collider to a 270 kilometer collider. Okay? You get back to the same problem of linear colliders, where we said 54 kilometers is bad, 270 kilometers is really, really bad in terms of tunnel cost. So it's not that easy to just say, let's build a high energy PP collider. Okay? You have to do some sort of optimization between R, E, and B.
Did I remind you to switch boards?
Oh, sure. So if we want to optimize the synchrotron condition, we have to go beyond just choosing whatever R, E, and B, and we have to take into account what technologies are available to us and how much cost we can actually accommodate in terms of making a larger collider. So for instance, if we wanted to build the FCC HH at CERN, okay, as I said, we can't change the order of magnitude on the magnets. That would be essentially impossible right now. We can't change the size by order of magnitude. That would blow up the cost infinitely. And ironically, at CERN, you have a geology issue, okay? CERN is set between two large mountain ranges, so tunneling costs aren't just the size of the tunnel, it's what's the material that you go through. So CERN is pinned in to say that the circumference of the FCC, they can roughly make it about as big as 100 kilometers, okay? Turns out to be 91 is the current optimum that they've come up with. But what this does mean is that you can't just keep the same magnets. We're going to have to increase the magnetic field to actually accommodate this. And to accommodate the FCC, you need a B field that gets up to about 16 Tesla. Now, it's not an order of magnitude compared to our 8 Tesla dipoles that we currently have, but it's a factor of 2. And now the irony is that even though the physics tells us we'd like to build a high-energy PP collider, it could do all the physics of a low-energy E plus E minus Higgs factory. The irony is it's not that we wouldn't like to do it. The problem is we can't. Currently, the technology does not exist. E plus E minus colliders are actually really, really simple things. They're just RF cavities. You just keep stacking them over and over again. You don't need super high magnetic fields. You just have to accelerate the particles. Here we need 16 Tesla dipoles. And what this corresponds to in magnet R&D, they project at least 20 to 30 years to be able to even come up with dipoles that you can manufacture, okay? Because you don't want to make a one-off. You need to make thousands of these things that's inside your tunnel, okay? Yep.
I've heard that right now, for whatever reason, the currently in these accelerators, they're only using type 1 superconductors for both the RF cavities and the magnets.
Actually, most are type 2.
Oh, okay.
But one way to go forward, so right now they're using kind of the best superconductors that you can build, niobium-310. One way that you could have a leap forward is develop high temperature superconductors, okay? Because you make these magnets out of windings. So that's possibly a way to cut down on the budget, the power consumption. But again, this is not like infinitesimal research that we're just around the corner. This still requires a lot to get to. So that explains why the time scales jump from the LHC to these high energy colliders. Now, 2070 is a lot longer than 20 to 30 years from now, but that also comes from the fact that the current way of thinking about the FCC for CERN is to redo the playbook for a LEP in the LHC, where first you build a tunnel and you can put an E plus E minus collider in, you got to run that for a while, and then you put on FCC-HH. Okay. So that's why you have these enormous timescales. Now, as I said, though, it's not just about getting to these high energies. We have the issues of the detectors, okay, and the large backgrounds as well. So even though we have these lovely dots for SPPC in China or FCC-HH at CERN, the real problem is, even though we talk about these like this is the next project for high energy, there's absolutely no guarantee that we'll actually get there. And what do I mean by this? Even if we could build the magnets, these 16 Tesla dipoles that get us to this technology, we have two other big issues. Because they're PP colliders, we have a large fluence and dose for our detectors, okay, the radiation dose from these particles. Okay. My cross sections are going up. I also need to increase the luminosity. And roughly, this is a factor of 20 times the high luminosity LHC. Okay? Now, if any of your Collider Pheno people that are familiar with the LHC, you know that they've had to replace the inner trackers of these machines several times, because even at the LHC energies, you're still killing off your computing for tracking your particles. This is not like a magnet or an accelerator, okay? This is kind of a bit of a darker art. You need to develop rad-hard technologies that can stand another order of magnitude or two, okay? So this is not just winding better or choosing a better superconductor. This is actually trying to think about how do you make a tracker that doesn't just immediately get burned on the second you turn on the machine, okay? The second part of this is, as we talked about last time, the detectors have to be much larger. Okay. So there are technologies beyond just rad-hard. You have to make a magnet that has essentially twice the aperture and twice the field strength. If any of you have ever seen CMS's magnet, this is kind of a one-off in the history of human civilization right now. We've lost the people that know how to do this, and now we want to build something twice as big with twice the field strength. There is no linear extrapolation to saying, I know exactly when I'll be able to do this, okay? So these are two important points that don't get brought up enough, which is even though we in principle have the ability to keep taking protons to higher and higher energy with synchrotron colliders, we don't know whether we can get the physics out, okay? So it's absolutely crucial from this perspective to think, are there other options? Now, some people kind of stick their head in their sand and say, well, this is 2070, okay? Who on earth knows what's going to happen 50 years from now? I'll be dead. Everybody else in this room will be Tom's age at that time. And I mean, who is actually focusing on this in too much detail? So it's like that kind of the cartoon of like, then a miracle happens here on the blackboard, right? There's lots of room for miracles in 50 years. As a physicist, I would not like to give up on the idea that we still want to search for what's happening in the universe at the shortest distances. So putting all our eggs in the baskets of PP colliders at high energies is kind of really dangerous to the field. If it doesn't work, we're just stopped. So what we have to do is we have to go back and think about where our limiting technologies were. So if the danger to a high energy PP collider is can we get the physics out, and the fact that the size keeps increasing, this is a 100-kilometer scale. This is, for instance, FCCEE is roughly a 17 billion Swiss franc project, okay? That's not FCCHH, you add another order 20 billion on top of that, okay? These are huge numbers in terms of physics funding, okay? So if we think about the bottlenecks for PP, it's going to be the size, and it's also going to be the backgrounds / the fluence. So one way to get around both of these is if we could actually build fundamental particle colliders, okay? E plus E minus colliders got rid of the background fluid issue, okay? Because you're just having two fundamental particles collide, you don't get all this detritus and all this extra radiation. They also potentially can solve the size problem in the context of, since if I want to probe a certain scale with the proton collider and I only get to use a fraction of its energy on average, if I have a fundamental particle, I collide them, I get to use all of their energy, okay? So you could scale the size by roughly a factor of an order of magnitude compared to a PP collider, theoretically, and you'd immediately get rid of the background fluence issue. The problem is that E plus E minus colliders, we ran into two issues. For our linear colliders, we ran into the issue of size and cost and power consumption. In the circular colliders, we just gave up on because of synchrotron radiation. So it turns out there are two possible technological solutions to each of these problems. So our issue with size, cost, right? This was all based on the fact that we had a maximum gradient that we could get to, okay? Our RF cavities, we use this fixed structure of a conductor, and conductors have this breakdown that implied roughly a maximum gradient. That was order 100 megavolts per meter, okay? And it's actually a little less depending on it. 100 megavolts is really pushing it, okay? So one way to make linear colliders work would be to have an option if you could increase the gradient. And we're not talking about increasing the gradient by a factor of 2 or so. If we really wanted to scale these things, we would need to increase the gradient by an order of magnitude or more. Now, since the thing that sets the maximum gradient is the actual copper accelerating structures or superconducting accelerating structures that we have, we need to come up with another accelerating structure, okay? It needs a new accelerating structure. To avoid the RF breakdown, okay? So there are potential ways to do this. One way to do this is what we'll talk about briefly, which is called Wakefield acceleration. Okay. Now, on the other side, even if we do this, linear colliders are still going to be power hungry. You still have to have the acceleration the whole way. They're still going to be sizable. Even if I change this gradient by an order of magnitude, we're at order 100 kilometers or so, okay? So it's still going to be big. This isn't something tiny. Circular colliders would be great because we can just keep using the same accelerating structures over and over again, but we are stuck with the fact that we can't do it with electrons. So in comes the muon, okay? So the muon in principle is actually pretty straightforward in the sense that it's a charged particle. We can use all the same accelerating structures we had to bring it up to energy. The only problem is that in its rest frame, the lifetime of a muon is about 2 microseconds. Okay. Now, should this matter or not, to give you a kind of a time scale, the LHC to inject protons using that LINAC, the 3 boosters to the LHC ring, the time scale for acceleration is about 20 minutes. Okay? So we have a problem of time scales. Yeah.
20 minutes in whose frame?
In the lab frame. Yeah. So these are 2 potential ways, and now I want to talk about them briefly. As I said, I really could use one more lecture, but we're going to get through a little bit just to give you a taste and appreciation for these things. So let's start off with Wakefield acceleration. Now I want to emphasize, these are not new ideas, okay? Both Wakefield and muon acceleration ideas have been around since the 60s and 70s, okay? It's how do we make them work is the challenge. But the basic idea is for Wakefield acceleration, since any cavities, any fixed structure I make has a breakdown voltage because I have this fixed structure and I'm putting some potential across it, the idea is to use something that's essentially structureless to start, okay? So we're not going to just put a large potential across 2 conductors like we've had the problem in all of our acceleration mechanisms so far. So the basic idea is we'll start with some quasi-neutral plasma. Okay. And okay, this plasma is neutral, so it's not obviously accelerating anything. Okay, there's no electric field over it. But if we take a plasma with all these particles doing their thing, the electrons and protons inside of it, okay? And if we take the plasma and we insert some sort of electromagnetic field disturbance. So the idea is we can do this in one of 2 ways. we can either take a plasma and shine a laser on it, okay, to make your disturbance, or you could actually take a charged particle beam, like an electron beam or a proton beam, and shoot it through there. So these two different ones, you'll see things called plasma wake field acceleration and laser wake field acceleration. I mean, they're both plasmas. The only difference is when you talk about plasma wake field acceleration, you're really imagining an electron drive beam or a proton drive beam that makes a disturbance. Now, when you make a disturbance that comes through here, what happens is that's going to separate your charges, your heavy ions versus the electrons. Okay? And so what you're essentially doing by putting a disturbance is you're creating a potential difference. You're creating a gradient in this plasma. Okay? Now, of course, if you just shone this on a specific cell, you take any electrons that were left behind, they get accelerated a lot. But the trick is we're going to send some disturbance in, and then we're going to send a beam of particles, electrons, right after it. So you'll create this disturbance, and then the electrons will feel this disturbance, and essentially that's why it's called wake field acceleration. It's kind of like surfing, okay? But the nice thing is, because you have this negative and positive particles in your plasma originally, you get a large gradient in terms of the electron side and the positive side from your ions. Now, because there is no structure, no fixed structure that you're putting a potential across, you don't have this limit on breakdown voltage, and essentially what you get is that the electric fields you can create on this are roughly 100 times the square root of the number density of electrons in your plasma, where these are roughly like 10 to the 14th to 10 to the 18th per centimeter cubed. Okay. And what turns out is that you can get large gradients that have been demonstrated of order 1 gigavolt per meter to 10 gigavolt per meter. And possibly people have even shown up to close to 100 gigavolts per meter. Okay? Now, if we go back, and if I can't see the board from over here, but if we had that 100 megavolt per meter that we had for RF structures, what we can essentially gain is 1 to 2 orders of magnitude, realistically with these. So now you can take a linear accelerator, which you couldn't get on click with that wall, and shrink it down to a size, potentially, that you could build a linear collider at very high energies. Okay? Now, what are the downsides? Why haven't we already built one of these things? Okay. And I'll put some links to some of the US particle accelerator schools, because unfortunately we just don't have enough time to do this in any detail. But first off, we still have to build a sizable collider, right? We're still going to have to build something that's over 10 kilometers or a few kilometers. Okay? So the question is, we have to chain plasma cells together. To make a collider. Okay? Now, in the context of RF acceleration, this is very easy to develop the synchronization conditions, et cetera. You have a very rigid structure, right? That superconducting cavity is not changing inside. This is a highly nonlinear process of making these disturbances. And although you can make these gradients over very short distances, okay, trying to do this over and over again exactly uniformly for 10 kilometers is a project that nobody's been able to solve so far. Okay? So this is one of the issues. Okay? How do you chain it together to make an actual collider? Another issue is when we've talked about it so far, I've just blithely said make an E plus E minus collider. Okay? Well, it turns out that if you play this trick with positrons, where you create a disturbance and then you try to send a beam of positrons right after it, this, in experiment, has been shown that the positrons don't want to stay together. Okay? They get an accelerating gradient, but if you try to load them, they essentially just fly apart very easily. Okay? So it's difficult to create a beam. And then last but not least, since this is a linear collider, okay, even if I increase the gradient, I still don't solve the issue of the fact that I just have to keep stacking accelerating components together. So I have to have a lot of accelerating, which means I have to a lot of power. Okay? So for giving an example of current parameters, and these are all just rough numbers because no one knows how to do all these things yet. If you wanted to talk about, for instance, a 10 TeV plasma collider, you're talking about terawatts of power or more. Okay? So now we're talking more than New York City, and that's an issue. So this is a super promising technology. We should investigate all avenues, but both the US accelerator community and the European accelerator community kind of view these things as, yes, we're going to keep growing this, but we have no idea to really make a realistic collider before the end of the century. That's kind of the consensus right now. Okay. So plasma colliders are very interesting, but we don't know how to actually implement them so far. But as I said, sorry, go ahead.
Yeah, I was just wondering, so don't you run into problem, since you don't have vacuum when you see the beam, you don't have any problem with like position what's in the plasma, or is the plasma separated from
The plasma is confined in a region, and yeah, you just have these regions of does the thing explode and things like that. But yeah, I mean, this is, yeah, well, I also wanted to make one other comment that this has got actually a lot of research funding, and it should have a lot of research funding. But one of the issues is sometimes, as we do as theorists, we kind of go off in epicycles and what we think about. Because the accelerator community has been so factorized from theorists and experimentalists, these issues haven't kind of come to the forefront as much. So one thing that's happened in the US during the SNOMAS and P5 process is we've kind of understood a framework that we need to develop these things better. And that actually brings me back to the one collider that only one person I think had heard of, or no one. The half collider that Daisy has proposed. So one way to get around this would be to say, I don't know how to do positrons. I don't know how to chain it very far together. Let me make a Higgs factory using just E-'s accelerated plasma, and then E+'s accelerated conventional RF technology. Okay? So this is kind of the first step, but it's still not on the time scale of any of the other E+, E- Higgs factories. So it's still kind of a pipe dream. So the last option, and which brings me to my shirt and the stickers, is the concept of a muon collider. Okay. Now, the only thing that stops us from using conventional technology on muon colliders, as I said, it only lives a very short amount of time. Okay? So what this realistically is telling us is that even though it can be a very conventional collider in terms of accelerating structures, okay, right, there's absolutely no problem getting a muon to 10 TeV in the context of if I can get a proton to 10 TeV already, I could do a muon to 10 TeV if I can accommodate a short enough time scale for this. The real problem is what we think of as the luminosity of the particles, okay? Because even if I can stack particles with the density of the instantaneous luminosities we've been talking about, I have an issue that they're all going to decay away from me, okay? Now, unfortunately, this is the one thing that I really had to do short shrift on, but we need to think about what luminosity actually means, okay? So all particle colliders have some context of issues with luminosity. We want to increase this. So this is an example of if I think about having a bunch of particles with N1 particles in and some density of particles, and a bunch of other particles, N2, with some density of particles, I can do a simple calculation and assume the density is not constant, but let's assume the density is Gaussian in every direction. And then I can use co-moving coordinates to integrate over these Gaussians. And then what you get is a formula for the instantaneous luminosity, okay? What it depends upon is the number of particles that you actually have, and essentially how small you can squeeze the density of these particles, okay? Sigma x and sigma y, and then how frequently you do this and how many bunches you can stack in your collider. So it turns out that this quantity that we always come up with is roughly 10 to the 34 centimeters squared per second, what you really need to do is have these things are limited essentially at the level of 10 to the 12, 10 to the 10 to 10 to the 12. If you try to stick too many particles in, like remember, if we're saying I have an electron beam or a proton beam, these all have the same charge. You stick more and more particles of the same charge, they want to fly apart, okay? So we start getting space charge effects when we try to put too many particles in. So the only other way you can do it is to try to squeeze the size of the beam. And to give you a context for how squeezed these beams are, we're having order of 1 trillion particles that are within a micron, okay? That's the scale that gives you that 10 to the 34 number. The way you do that is you have to have lots of magnets to focus your beam and keep it tight. And then at your interaction point, you have to have very strong focusing magnets as well. Unfortunately, because we're running out of time in the context of a larger scheme, this is a very interesting subject in terms of everything we've talked about has been imagining one particle going around. If you imagine a beam of particles, there's a spread of energies and momentums. So you really need to think of this phase space in 6 dimensions and how do you cool this phase space so now you're only a micron and everything has the same energy, okay? This is a very interesting topic and that gets into the well beyond Jackson version of E&M, okay? But for our perspectives, we just need to squeeze it. But the problem is muons have 2 things going against them. First, they're unstable, so they don't live very long. The second is because they're not just sitting around that I can like go to the store and buy a can of helium, I have to make muons, okay? And so we need to make our muons, okay? Now we actually have to secretly do this for positrons as well. There's no positron store you go to and build these. So all these colliders have essentially another collider or another LINEC with a fixed target to make the antiparticles. The difference is that for positrons and for antiprotons, since they're stable particles, as long as I magnetically confine them, I can make the beam what I want it to be. Muons don't live very long, and when I make a muon beam, where I typically take a proton linear accelerator and I hit a fixed target, I make, for instance, a delta resonant that goes to pions that then go to muons. This actually is the same thing as Dune, right? We're making a neutrino beam this way. The problem is the beam is roughly the size of a beach ball, okay? So I make a beach ball that I confine using a very strong magnet, and I have to turn a beach ball into something that's kind of the width of your hair, and I have roughly 2.2 microseconds in its rest frame, okay? So this is a very challenging concept, and this comes down to the concept of cooling particle beams. So why do we call it cooling? As I said, you have this 6-dimensional phase space of all the x coordinates of the particles and all the momentums of the particles that you want to put in. And so you have to do this regardless of what type of particle you're doing. A proton or electron, you have to cool the beam as well so that all the energies are the same, all the positions are the same. But the typical techniques are either for electrons, you can do, since they live forever, is you stick them into a synchrotron ring and you let them just have synchrotron radiation and you essentially damp the energies, the outliers, okay? But that takes a while. Another technique is called stochastic cooling. All of these things I'm saying also, by the way, got Nobel Prizes around the way. I mean, these are not just like, oh, this is something easy. These were breakthroughs along the way. Stochastic cooling essentially uses a feedback mechanism where you put it in a storage ring, you have a sensor to say, are there particles that are not at the energy I want? And then you can use a laser or some electric field to kind of kick those particles. Stochastic because you have to do this kind of one particle at a time. It's not a uniform thing. The problem is that these also are minutes or hours, okay? So you can't use this technology for muons. So the only way that people have come up with to do this is something called ionization cooling. It's very simple to explain. It's very complicated to actually implement as an engineering problem. The basic idea is you have a beam of particles that's going in every direction. You have your beach ball, okay? The momentums are also going in every direction because you're making collisions. They go out in lots of directions. Well, I can't cool these using the normal techniques, but anytime I pass it through a material, they're all going to lose some momentum. Okay? They'll lose momentum in every direction. Okay? But this is a very quick thing. Speed of light, speed of light. Okay? Now what I can do is, since they all lose their momentum, so this is the initial momentum, and for instance, this is a momentum like this, then I can put, after an absorber where they crash into, I put an RF acceleration cavity, and I only give them momentum in the longitudinal direction. So essentially what I'm doing is, by cooling, I am making this thing straighter and straighter, and I'm getting a collimated muon beam that comes out of it. Now, it's simple to explain. It requires no physics beyond beta block to understand the concept of ionization cooling. The trick is, how do you do this in an engineering problem? You have to have a magnet that's strong enough to focus all these particles to go through the absorber. Then you have to have an RF cavity, and you need to put these things very close together in terms of a superconducting magnet, a hot RF cavity, and you have to repeat this many times. Okay? But it actually is very simple physics. There's no magic appearing here. There's no nonlinear process. We know the concept of the cross sections. And it turns out that you actually can do this on paper. And this came for the first time in roughly 2014. Okay? Unfortunately, it's after the US had already stopped muon collider R&D. But in 2014, a US physicist, Dick Distrakakis, and Bob Palmer came up with the first realistic cooling channel design for how you could do this. Okay? Now, just like plasma wake field, this was an area where people were kind of doing crazy things and saying, hey, I could always do this if I had like 100 Tesla magnet or did any kind of rain, kind of blue sky sorts of things. In 2014, this was constructed on paper with all realistic accelerating gradients and realistic magnets. So we know how to do it. We just have to build it to see if it works. Now, the other thing is, the concept of luminosity that I had, this is still true. Even if I could cool the beam, okay, I'm still limited to roughly at this 10 to the 34 scale that all the particles are limited at. Okay? So if we need the luminosity to increase, and if I can't stick more particles in per bunch, if I can't squeeze them better unless I have some magnet breakthrough, the only way to do this would be to stick more particles in something more often. Stick more current in. If I need more current, that means I need more power, and then I run into power consumption issues. So the muon has one other trick which makes it advantageous, which if I look at the luminosity achievable per power, okay, so we have a number of different curves. This was from the implementation task force during SNOMES. And so these are our circular E plus E minus colliders. The luminosity over power just drops off because that's synchrotron radiation. Okay? Linear colliders, like ILC or CLIC, they're roughly constant, okay? Because I just need more RF. I need more power if I want more luminosity. Just got to put more current into it. The muons have this weird trick where they appear to get better and better, okay? And now what this trick is the fact it's nothing kind of like a machine trick. It's the fact that we get to avoid the fact that muons decay if I go to higher energies. They live longer in their rest frame. So muon colliders actually become more and more efficient the higher energy muon collider that you can build. Okay? So it's a really kind of cool trick to go about this. Now, I'm just about out of time. We only have a couple more minutes left. So I want to kind of give you this sketch. So,
what were the other colored boxes for? Like, especially, like, what are the green, yellow, and the gray?
So here are your PP colliders living way out here. So that's still roughly at 10 to the 34 and kind of constant. Eventually, if I went to high enough energies, I'd have a synchrotron problem, but not for a long time. It's just kind of roughly two numbers. Plasma wake field colliders are living here. They have this huge error bar because no one actually knows. Okay? These are numbers proponents put in, but the implementation task force was like, yeah, we don't believe you. So that's the other numbers. Sorry.
So as of now, sigma X and sigma Y are constrained by the powers of our focusing magnets. Is that correct?
Yep.
Do we envision getting better focusing magnets such that they will be limited by like having a bunch of light charged particles close together, or would we have to get like really, really good?
It's limited by the field strength we can put in our quadrupole magnets, and as well, you run into basically space charge effects that you not only need to focus, but you need to make sure that all the particles really are there. So there's kind of like the stragglers or whatnot can get into issue. Also for linear colliders, one of the issues is because you need to load more particles because you don't get these things going around and around and around, linear colliders tend to have a little higher bunch charge than other colliders. So what happens that linear colliders actually have a phenomenon called Beamstrahlung rather than Bremsstrahlung, where the space charges are so large of the beams when they see each other, they deflect and they essentially radiate, and you lose what the good luminosity is at the collision point, and they become harder to go at higher energies. So as I said, a muon collider is relatively straightforward except for this concept of ionization cooling. We have to smash things into a target so that we make our pions and our muons. We have to collect them. We have to cool them. But now the nice thing is everything after this is relatively straightforward in terms of technologies. And what the amazing thing that's come out in the last few years in both Europe and in the US is that we believe that the technology to do this is all within kind of order 1 technologies of what we have now, okay? It's not that you can go out and build a muon collider now, but the consensus is it's roughly a 20-year time scale to build one. That's why the 2045 on my shirt, okay? Now, of course, this doesn't mean you get money for it. What this tells you kind of technology skills. Now, I'm out of time, so I can't go through all the fun physics that you can do with it. But the nice thing is you can actually fit a muon collider in a much smaller distance than even the LHC. It's about 10 kilometers around. You can fit it on the Fermilab campus even. And I'll just flash these, and you can ask Matthew McCullough maybe when he talks about these things at the end of New Paradigms.